We'll implement the global field type in a module that uses the local field module. We'll prevent implicit typing, and we'll declare everything in this module to be private by default, in keeping with the information hiding philosophy of object-oriented programming. We'll then expose the global field type and any public type-bound procedures, and then we'll declare a private array co-array component to hold the solution values. Then we'll bind two private type-bound procedures for constructing new objects, set and only allocate. And we'll bind the public generic name global_field_, through which the test program invokes the constructors set and only allocate. The compiler will determine which constructor to invoke based on the actual arguments at the point of invocation. Next, we define two public generic operators through which we invoke two private type-bound procedures to accomplish the operations. Then we define our assignment that takes the final right-hand side expression result as a local field and assigns it to the left-hand side global field. Finally, we define a public type-bound procedure that will return the global field state, that being the private component values. We will also declare a few module variables and a constant that will be common to all variables of the global field type. We'll need to synchronize images in three places in this solver. Once at the end of each of the two object constructors, set and only allocate, to ensure the objects are there for other images to access, and once at the end of the user-defined assignment to ensure that the assigned data is available to other images. To maintain high performance, we will synchronize each image only with its two neighboring images because the one procedure that communicates data, the Laplacian operator, only needs data from its nearest neighbors. Now we define the first constructor, which sets the local elements of the values co-array based on the past internal and boundary values. It also does one consistency check and calculates the size of the data partition that will be local to this image and the size of the spacing between grid points, dx. Doing so involves an allocation of the co-array, which is an implicit synchronization point, followed by a call to synchronize after all the data have been established. Here is the constructor that merely allocates memory without initializing any data. The included co-array allocation provides another implicit synchronization point. I'm going to leave the implementation of the Laplacian operator as an exercise to the viewer. Those who viewed the parallel programming videos in this JOLT should now be aware of how to communicate data between images as necessary for evaluating the finite difference formulas at the edges of each image's subdomain. All operators bound to the global field and local field types can be implemented as pure functions, which ensures that the entire right-hand side expression evaluation that we saw in the test program in the previous video can take place asynchronously. There is no chance that any of the operators will modify state external to the procedure, and therefore no chance that any of the calculations of one image can affect those of another image. This is true even in procedures that need to communicate, as is required inside the Laplacian operator. Other than the constructors, the one place we synchronize is where we modify state in the user-defined assignment. We conclude with a procedure that returns the global field component data to the test program, which uses that information to check for convergence to the known steady state. I'll also leave the implementation of the local field type in a separate module as an exercise for the viewer.